This week we're going to talk about Chapter 6, which is all about discrete random variables. So we're going to start out with talking about what we mean by a discrete distribution or a discrete random variable. So we're going to look at specific examples: the uniform distribution, the Bernoulli distribution, binomial distribution, Poisson distribution, and hypergeometric distribution. And then there's a couple of optional sections in the text that we won't talk about, but should be straightforward if you do want to look at those. They're interesting: the geometric distribution, and then also transformations of random variables, which is actually something that's very useful, but maybe a little bit beyond the scope of what we're going to get into in this course. So here are the learning objectives for this chapter, and you can look at those on your own if you like. First of all, let's define what a random variable is. Random variable is just a function of a random experiment, or the outcome of a random experiment, that assigns a numerical value to the outcome of the experiment. The notation that we're going to use for a random variable is capital uppercase letters towards the end of the alphabet, like X and Y, and when we use a lowercase letter, that's going to represent an actual value that the random variable can take on. And a discrete random variable is one that has a countable number of distinct values. If you think back to Chapter 5, where we talked about probability, and we talked about rolling a six-sided die, and we said that was a discrete sample space. Well, now we're talking about how do you assign numbers to the elements of the sample space. Well, it turns out we do that by using what's called a probability distribution. And in the case of a discrete random variable, the probability distribution assigns a probability, or a number, between 0 and 1 to each value that the random variable can take on. And the following things have to happen, and this is very similar to what we did in Chapter 5. All of the probabilities have to be between 0 and 1, and they can include 0 and 1, and the sum of the probabilities has to be 1 over all the values in that sample space. So here's an example. If we're going to flip a coin 3 times, and we're going to count the number of heads and tails, then we can write out the sample space as follows. We either have 3 heads, 2 heads and a tails, heads, tails, heads, tails, heads, 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 tails, 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 heads, tails, and so forth. And we're interested in X, the random variable. Capital X here is the number of heads, and little x is the actual values that are observed. So how many heads are there here? 0. How many heads are there here? 1. Okay, so that shows up here, and then here, and then here. So there's how many ways can that happen? Well, there's 3 of those, and there's 8 possible outcomes. So the probability of seeing 1 heads is 3 over 8, and so forth. Probability of seeing 3 heads is 1 over 8. There's only one way that that can happen. And so we have 1/8 plus 3/8 plus 3/8 plus 3/8. That's equal to 1. We can make a plot of this, and a probability distribution is basically, at least for discrete random variables, basically like a histogram, and where we've got the probability on the y-axis, and we say how many heads do we have, and what's the probability associated with each of those. So 0 had a probability of 1/8, 1 had a probability of 3/8, goes over to here, 2 3/8, and so forth. Anytime we have a random variable, we are going to ask the question, what's the expected value? And the expected value is just another way of saying what's the mean value, or the average value. And we denote that by e of x. That just says the expected value of x, if x is our random variable. If y is our random variable, then it would be E of y. And we can actually write down what the expected value is by taking the sum of the x values times the probability of those x values. So multiply x times the probability of x, sum those things up, and that's what we're going to call the expected value, mu. And this is the same expected value that we talked about earlier in the course when we were talking about the population mean, or the expected value for the population. And this is a measure of central tendency. So this tells us where the middle of the data is, at least in some sense. Here's an example using service calls. The distribution of Sunday emergency service calls by Ace Appliance Repair is shown here. Probability of 0 service calls on a Sunday is 5%. So if I want to calculate the average number of calls per Sunday, what do? I take 0, multiply it by 5%, and I get 0. The probability of 1, so here x is 1, the probability of that is 10%, so I multiply 1 times 10%, I get 10%. 2 times 30% is 0.6, and so forth. Fill all those things in, and then notice the probability sum up to 100%, and x times p of x sums up to 2.75. So this is the average number of service calls per Sunday for Ace Appliance Repair. Notice that 2.75 is not one of the values that the random variable can take on. They don't get 2 3/4 of a service call ever. So the expected value doesn't necessarily have to be one of the values that your random variable can take on. It just says in the long run, if you were to do this over and over and over again, you would have on average 2.75 per Sunday. So we can look at a plot of this. Here is a density plot or probability distribution, and the average value is right here at 2.75. And one way to think of the average or the mean is to think of the point that balances all of the data. So this is a non-symmetric distribution. These values over here are much smaller than these values over here, and there's no symmetry here. But you might say, where would I put a fulcrum if I were going to try and balance all of this stuff out? And it turns out that 2.75 is the point that would give us the balance all these things. So that's another way to think of the expected value. So as before, when we talked about characteristics of the populations, we said first we have the mean, or the measure of the center, and that's the most important one. And then we followed that up with talking about the measures of variation, and we talked about variance and standard deviation. Well, we're going to do exactly the same thing here. The variance of a random variable, discrete random variable, is just the expected value. I should write this. The expected value of x minus its mean quantity squared. So we're going to use the same operator that we used before, but instead of putting just an x in right here, we're going to use x minus mu. And so that's what you see right here. This part, x minus mu squared, I should say, times the probability of x. So what we're doing is we're saying how far on average is x from its average, from the average of the distribution, square that distance, and then weight it by the probability associated with each of those x's. And this is the main measure of variability that we're going to use in this class. And we talked about the empirical rule and Chebyshev's inequality and some of those other things. And those are all in terms of means and variances, or means and standard deviations. And so to get the standard deviation, all we're going to do is take the square root of the variance. Positive square root, that is. So just to give you an idea of how you would do this, here's another example. We've got the Bay Street Inn has 7 rooms, and it's in California, and it's nice and sunny there all the time. And so of the 7 rooms, you could say what's the probability that each of those is filled on any given night. And so we've got X is the number of rooms that are filled, and it goes from 0 to 7, and we get the probability associated with each of those. So to get the mean, we'll just take X times P of X, sum all those things, and the mean turns out to be 4.71. But to get the standard deviation, what we need to do is take X minus mu. So now that we got the mean, we can subtract that from X. And so we have 0 minus 4.71 is negative 4.71, 1 minus 4.71, and so forth. And then I'm going to, instead of averaging all these values, if I average these values, I'm going to get 0. We're going to square those values and then take the average of these according to the weights that are given here. So we're going to take 22.1841, multiply that by 5%, and we get 1.19205. To do that for all those, sum them up, and that gives us the variance, sigma squared. So in order to get the standard deviation, all we do is take the square root of that, and we get a standard deviation of 2.05. So let's look at a histogram of this data. Here we've got all of the probability density, we call this, and we can say what's the mode. The mode is 7. That's the one that happens most often. But the average value is 4.71, and the standard deviation is 2.06, and that tells us something about the variation around the average value of mu. Now this is the type of data set that you would use if you were going to try and get a bound on the proportion within a certain number of standard deviations. You would use Chebyshev's theorem instead of the empirical rule, because this is clearly not a bell-shaped symmetric distribution. But the important point here is that this is a distribution. This is a population distribution. And now we're going to come to the meat of this video, and that is defining what's called the PDF, or the probability density function, and the CDF, or the cumulative distribution function. These are both very important things that we can use, tools that we can use for determining probabilities associated with the discrete distributions that we're going to talk about in the next videos, the uniform, the binomial, and so forth. So the probability density function just shows us the probability of each value of x if we're going to plot it. We don't always plot it, but here's an example. This is a probability density function. Here are the values of x, here's the probability associated with each of those, and so this is the PDF in graphical form. We don't have to write it out in graphical form. In fact, if we come back and look at this, you would say this is the PDF for in non-graphical form. So I know what x is. Here's x and the probability associated with that x. And so my random variable is completely defined by this probability density function, or PDF. And so I could say, if I want to know the probability that x is equal to some number, I can just go and look it up with the probability density function, and we'll see that these things can get a little bit more complex as we move on. But the next important thing that we need to keep in mind is what the cumulative distribution function tells us, or the CDF. And this is a function that adds up the probabilities, just sums up the probabilities going from left to right, or smallest value of x to the largest value of x, and just add those probabilities up as you go. And this is a very important concept, not just for discrete random variables, but especially when we get into continuous random variables, which we'll talk about next week. So here's an example. This is fake data, it looks like. We've got x and the probability of x, so the PDF says what's the probability that the random variable capital X is equal to the little value of x, and this is a symmetric bell shape, not that that matters, but we come in here and say what's the value of, or what's the probability that x is equal to, say, 6, and we come up here and we could write that down. We'd have a table somewhere to tell us exactly what it is, but that's the idea behind the PDF. The CDF says, well, let's add these probabilities up as we go. So we're going to start over here and we're going to go this direction, and every time we hit a new probability or a new number, we're going to say let's add that probability. So here we have at 1 there's no probability for 0 and 1. The first one comes in at 2, and so that's this value here, put right here. Now this scale goes up to 100%, this one goes up to 25, so that's why it looks like it's smaller. It's actually exactly the same size. But then once we get to 3, we're going to say, well, what did we have before? It was 2 plus this value here. So that gets added on. When we get to 4, we're going to say, what did we have before? We had 3 plus, we're going to add in this value. And so you get this kind of nice looking S-shaped curve that goes up to and approaches 1 eventually. So the difference here is the CDF tells us the probability that capital X is less than or equal to little x. And so we've got to keep in mind that the endpoint here, the fact that we're saying less than or equal to, that's an important concept. Okay, so we're going to use these two functions quite extensively in this course, and so make sure you understand them, and when we get to the next videos you'll see where these things come into play, and we'll be able to calculate probabilities associated with different random variables using these things. So we will see you in the next video where we talk about the uniform distribution.